We have Adam Rumpf from Florida Polytechnic University sharing his story of going from a math avoider to a math curator, how mathematical modeling changed my life. Take it away.
Well, thank you for having me here, and thank you to everyone for arriving. So just to explain a little bit about who I am first, my name is Adam Rumpf. I recently completed my PhD in applied math from Illinois Institute of Technology, and I'm a first-year instructor at Florida Polytechnic. I just started last year. This is my first full-time teaching position that I've had. I was asked to give a talk today about my math background and my career path up until this point because I suspect that it's quite unusual for most mathematicians. In particular, it's definitely not something that I was always interested in. I'm jumping around the slideshow. Sorry about that. Today, math education really is my life. It's what I would be doing as a hobby, even if it weren't my actual career. I enjoy making demonstrations and animations and showing cool math stuff to people. That's why I'm a math instructor in the first place. But it definitely wasn't always that way. Like a lot of people, I was not particularly interested in math in high school. So I'd like to talk a little bit about the long and meandering path that ended up taking me to where I am today. I'll admit that I didn't always really have very good or strong reasons to do the things that I did while I was a student and to study the things that I did. And it's sort of by random chance that I ended up in applied math eventually. It's definitely the right thing for me now, but there were a lot of contingencies along the way. And a lot of what I'm trying to do now is to help make it so that luck is not a necessary component for getting to the right career. So we all know what the public at large thinks about math. Like, I suspect that most of the people watching this presentation really like math and are interested in it. And when they think about what math is, they're thinking about mathematical modeling, fractals, high dimension spaces, cool stuff. That's not what most people think of when they think of math. They think of crunching numbers and solving equations, and that's understandable since that's all that most people see of math. It's not really until you get to the advanced stuff that you learn that math is actually interesting. I don't want to oversell the transition that I went through. I didn't go from hating math to liking math. I was mostly ambivalent towards math throughout most of my academic career. I grew up in Michigan, and I went through an advanced pace math and science program while I was in high school because I really liked a whole bunch of different areas of science and technology, and I was okay with math. I definitely didn't think of it as a viable career option or as something that I was particularly interested in studying for its own merits. It was more just that I understood that it was an important component of studying science. And it was something that I was okay at doing, but I wasn't really particularly interested in it. So when it was time for me to start my undergrad degree, I decided I wanted to try living somewhere very different. And so I went to Arizona State University. My original declared major was architecture because it seemed to me like that was a combination of art and science. And I really liked design. I still do. That's why I make games and demonstrations and things. A lot of architecture programs, though, like at the time I was looking at them and they seemed a little bit wishy-washy to me. Like they focused a lot on the design element and not very much on the structure element. And that seemed sort of the wrong way around as far as I was concerned. So before I actually started my freshman year, I switched to the civil engineering program. And that was my major for 2 years. So I had some engineering courses and I went through the engineering sections of all the core math courses. So the engineering calculus sections, engineering linear algebra, engineering differential equations, statics, dynamics. Engineering sections of those courses are usually taught in a very utilitarian way. They teach you about methods as tools for your tool belt, and that's about it. You never really get into why they might be interesting on their own merits or what you might use them for outside of engineering. And that was quite a lot of math that I ended up taking in my first 2 years, and I got a little bit burnt out. So I decided that I was done with math, that engineering wasn't for me, and I wanted to quit taking math classes. So I did. So I switched to being a geology major for my junior year. But because I had been an engineering major for 2 years, I had way more math classes than geology usually requires, and it was pretty close to having a math minor. So I decided just to avoid having all of those classes go to waste, since I only needed a couple more classes for the minor anyway, I might as well just take a few more and get the math minor along with the geology major. Part of that entailed taking a couple of upper division math courses like real analysis, which were fun and interesting, but certainly did not seem useful to me. At the end of that year, it seemed fairly evident that geology also was not quite for me. It's something that I'm very interested in, and I really like it because it's a very impure science in the best way. Like, it incorporates elements of physics and chemistry and biology, and I like all of those things. That's one of the things that attracted me to geology in the first place. But I also ended up doing a lot of field work and stuff with hand samples, and that wasn't really something that interested me. And I certainly didn't see myself as being a professional geologist. So I started looking for options for what I could do my senior year. I only had 1 year left on my scholarship, so my options were quite limited because I needed something that I could complete with all of the courses I had in just 1 year left. And it turns out that Arizona State had just 1 year prior to that started their own applied math program. They'd had a pure math program for many years, but they had just started an applied math program. It was one that was specifically focused on mathematical biology. So compared to a lot of other applied math programs, it had a lot of science prerequisites and not as many math prerequisites. So it was something that I could actually viably switch to, and I had time to complete it in the year that I had left. And so I did. For my last year, I switched into applied math and essentially traded my major and my minor. So the full name of the math program there is Applied Mathematics for the Life and Social Sciences, which I like to call aimless, and that seemed appropriate given everything that had happened in my career up until that point. I originally joined it for purely pragmatic reasons because it was something that I could do, and because applied math seemed like it would be something useful to know about for someone like me who's just generally interested in a bunch of different areas of science, but who doesn't really want to have to commit to just one of them. And even to this day, that's still the main reason why I would give, if I was trying to convince a student why they should study applied math. It's because it's required in all of these different STEM areas. So if you study applied math, you have the flexibility to study problems in whatever area you want to, and to switch between different areas if you want to. But part of that program also involved taking a couple of mathematical modeling courses in my last year, and those, it turns out, were actually very fun and interesting. And they had sort of showed me for the first time that math was something that is interesting to study on its own merits. And I would count this as the first of two really important classes that sort of ended up turning around my perception of what applied math was. Again, this program had a major focus on biology, so we studied a lot of population and epidemiological models, and there was a major focus on trying to present math in the way that people actually use it in the real world, which is often very messy and is very much driven by the kinds of questions that you might want to ask about the model that you're looking at, and not necessarily having to care about proving things or getting precise answers, but approximate answers are okay sometimes. Graphical methods for just quickly seeing how something behaves are okay sometimes. Still, at the end of that program, though, I wasn't really sure what I wanted to do for a career, but the person who ran the program also ran a summer program, which is called the Mathematical and Theoretical Biology Institute, or MTBI. It goes by a different name now. But basically, that's a 6-week summer program in Arizona. Arizona in the summer is not fun, but but he tried to convince me to check it out. And it's essentially meant as preparation for people who are going into graduate school. It's 3 weeks of intensive coursework, and then you break off into teams of students to pick a research project and work on it for the next 3 weeks. And at the end of it, you build a model, you write some programs, you come up with some results, and then you come up with a technical report and present that. Our particular group decided to work on modeling an avian disease back when epidemiology was just a fun thing to study theoretically and not all too real. The program was exhausting, but also a lot of fun. And it gave me a lot more experience in the way that people actually use mathematical modeling in the real world. And yet still at the end of it, I wasn't really sure what I wanted to do as a career. Research seemed very hard, and I wasn't really sure that I wanted a career that would involve mostly doing that. So I decided to do what most undergrads do when they don't know what they want to do as a career and they want to avoid growing up for just a few more years. I applied to grad school. So I applied to some applied math PhD programs, and I was accepted to the applied math program at Illinois Institute of Technology. And just to be clear, that's a terrible reason to apply to grad school. Grad school is a huge time commitment, and it somewhat limits your career options. So you should really only do it if you're sure that you're going to be going into academia or research. And I definitely wasn't at that time. Part of that program involved choosing between a few different focus areas. One of them was discrete math, which I decided to go into for no real reason because I didn't really know what any of the focus areas were at that point. And one of the courses I took during my first semester was something called graph theory. And I didn't really know what that was either. I assumed that it would be something to do with graphical methods for maybe analyzing dynamical systems or something. That's not what graph theory is. Graph theory is actually the study of what most people would call networks. A graph is just a bunch of stuff that is connected, and graphs are fantastic. You can use them to model all kinds of real world things. They describe road networks and infrastructure networks and social networks and more abstract things like conflict networks for timetables. And there are all kinds of things that you can do with them, like finding paths through them, figuring out the optimal way to route material through them. They're the way that traffic engineers solve a lot of problems. They come up a lot in computer science. They're a great modeling tool. And so I was in this course and we had gone for the first few weeks just sort of like drawing what looked like children's puzzles on the board. And I was waiting for the day when that part of the course would end and we would start writing down equations and functions and computing things. But that never happened because it turns out that what I didn't know before that point is that about half of math is not really about quantity in the way that something like calculus or algebra is. Graph theory is the first course that I took that was about studying structures rather than quantities. So it's an area of math that you can be good at, even if you aren't particularly interested in numbers. A lot of people, I have said to a lot of people over the years that I'm a professional mathematician, but I don't really like working with numbers. And they usually think that I'm kidding. But I'm not. What I'm talking about is this kind of thing. This is the kind of work that is a little closer to what most applied mathematicians actually do. And it was the second of the two courses that I think were essential in turning around my perception of what math really is, because it was so completely unlike anything that I had ever taken before. And this class, more so than anything else, really showed me how broad and varied of a field math is. Most people think of it as being very limited and static, but when you see something as different as this, I think that goes a long way towards showing you all of the other things that math can be. Also, while I was a grad student, I was working as a teaching assistant. Part of that involved running our calculus labs and recitation sessions. At IIT, they use Mathematica for all of their calculus labs. So I had to learn that rather quickly during my first year. I had some programming background, and Mathematica is very easy to pick up. It's made for mathematicians who don't necessarily know that much about programming. But what it's really good at is making graphics and interactive demonstrations. So I started to do that for use in my calculus labs and my recitation sessions, just to give things to show students. But that turned out to be a lot of fun, and it seemed like a useful tool for learning about other things myself. So I started using it to just explore other mathematical things that I was interested in, and that got a little out of hand. In the years since then, I've accrued, I think, over 200 Mathematica demonstrations just for fun because I wanted to make them. And all of those things are available as open access on my website. And that's kind of the thing that eventually led me into wanting to be a professional math educator. I want to show cool math stuff to people, and that's what I get to do now. It's what I would be doing as a hobby, even if I weren't an instructor, but this gives me an excuse to. but part of why I decided to go into math instruction is also because of thinking back to like the way that I thought about math when I was in high school. And I imagine that a lot of people are in the same situation that I was in then, where you know that you're generally interested in a bunch of different branches of science, but you still don't really know what math is yet, because how could you at that point? I happen to get very lucky and just to sort of stumble into the right classes at the right times, but I don't think that luck should be a requirement for learning what math is. And I would like to try to make some improvements in that area. It is still my first year, so I will admit all of this is still a work in progress, and I still don't know the best way to approach everything, but there are at least 2 lessons that I try to take with me just based on my own experiences into the classes that I design. And the first is what I learned when I took those mathematical modeling courses, and that is just to try to make an effort to present math in the way that it is actually used in the real world in something like mathematical modeling, and to shift some of the focus onto things like how to translate between a real world system and the abstract mathematical system. And just knowing that sometimes things get messy, and that's okay. You can show complicated mathematical models to students even at a very early level. You can show them dynamical systems models even if they're in Calculus 1, because if you know what a derivative is, that's enough to understand a differential equation. And I think there's a lot to be gained by showing these kinds of things to students as early as possible. And sort of on a related note, the lesson that I take from having had graph theory when I did, I think it's very important to also try to impress upon students how broad and varied math is by showing them some of the things that they get to look forward to in the future, showing them some things that lie beyond the scope of the course that they're currently in. There's a lot of cool stuff just sort of sitting right next to the things that you usually cover in the course. And I know that it's hard to, because everybody's under time constraints and you have this list of things that you need to cover on the syllabus. But I genuinely think that it is important to try to impress upon students what math really is and what it's like and all the cool stuff that there is out there, and to take some time to stop and smell the roses. If you're in Calculus 2 and you're talking about sequences and series, just take a little bit of time to show some fractals, because you can analyze them using sequences and series, seeing why some of them have infinite perimeters and why some don't. Those things are defined as series. And it's the kind of thing that a student can look at and just appreciate on its own merits. So something that I'll be looking into doing, hopefully in the years to come, is to try to find ways to give the students more things to do in class and more things to play with. In particular, what I'd really like to do is to try to shift some of the focus away from just lecture material and towards giving them projects and some early experiences in mathematical modeling. That's one of the reasons why I joined Semiote in the first place, because that's exactly the kind of thing that I would like to try to incorporate into my own classrooms. So hopefully this has been informative for you, and hopefully I've given you some insight into the situation that a lot of your students may find themselves in. In case you would like to look upon my works, this is my website, or you can just search for my name. I upload everything that I make just as open access, open source. So you're free to use whatever you want for whatever purpose you want. Thank you all very much for attending. And I guess I have some time now to answer questions.
Thank you, Adam. Thank you. That's really interesting. Questions?
Hey, Adam.
Oh, hello. Who is this stranger?
So I thought you could, if you wanted to share the story, I'm kind of interested in the story behind your symbol. Because I know the other day we talked about, I just had taught the 7 bridges of Königsberg, and I thought, hey, that symbol looks a lot like that graph. So is that a story that you could share with us about why you thought of, well, having the 6 bridges?
Yes. Yeah, let me bring it back up. This is my logo that I use for all of my stuff. It's something that I came up with while I was in grad school. And as you've observed, it's based on the 7 Bridges of Königsberg puzzle, which is, the reason why I picked it is because it sort of seemed like a good combination of all of the things that I had learned in grad school. Because it is in some ways the first ever graph theory result. It's about Eulerian circuits, which is the first ever result that Leonhard Euler proved, and he had to invent graph theory to solve that puzzle. So that's sort of related to me taking that first graph theory class, which is sort of what introduced me to graduate level mathematics. But it also describes a civil infrastructure network, because the picture is like an abstract representation of the 7 bridges in the city of Königsberg, which is related to what I eventually did in grad school, which was civil infrastructure network optimization. So that just seemed like a nice compact symbol to describe everything that I had done in grad school. And if you're wondering why one of the lines is broken, that's because famously the original puzzle is not solvable. What you're trying to do is traverse the entire graph in a way that covers every edge exactly once. But it becomes solvable if you remove any of the edges or add any of the edges. So I didn't want to give myself a symbol of an unsolvable puzzle, so I altered it slightly.
That is really cool. Thanks for bringing that up, Jared.
Mm-hmm.
I really appreciate hearing your story. And I can think of students in my classrooms who are probably in one of those phases as well. And I'll probably point some of them to the recording of your talk, if you don't mind, once it's posted on Simeode. This is students need to be hearing this too. It's valuable as faculty to hear a variety of stories, which are different sometimes than our own. But yeah, I'm sure your students are really blessed to have you as an instructor, and then I'll be sharing with some of mine too.
You get a variety of opinions. But
Sorry?
I think you get a variety of opinions from them.
Mm-hmm.
But thank you. I appreciate hearing that.
Awesome. Okay, well, let's thank Adam again.